సబ్స్క్రైబ్ చేయండి. ఫర్ మోర్ అప్డేట్స్ బెల్ ఐకాన్ క్లిక్ చేయండి.
Now we are going to discuss Planck's radiation formula. The Planck's radiation formula or Planck's law of energy distribution. First of all, we have to study the Planck's assumptions. The black body radiator contains simple harmonic oscillators which can vibrate with all possible frequencies. For example, so this is the black body. For example, this is the black body. The black body radiator contains simple harmonic oscillators. Simple harmonic oscillators which can vibrate with all possible frequencies. With all possible frequencies. So first point is the black body radiator contains simple harmonic oscillator. This is the simple harmonic oscillators. Simple harmonic oscillators which can vibrate with all possible frequencies. With all possible frequencies. Our second point is the oscillators are of molecular dimensions. So same as molecular dimensions is equal as oscillators. So third one is the oscillators can't emit or absorb. So oscillator can't emit and also absorb energy continuously. So the oscillator can emit and absorb, but not continuously. And the fourth point is the emission or absorption of energy takes place in discrete amounts H values, not E values. So emission or absorption energy takes place in discrete amounts E values, energy values. So here energy is we know that here energy packets like as h nu. H is the Planck's constant, nu is the frequency. Now we are going to derive the Planck's radiation law. Emission or absorption of energy takes place in discrete amounts the values of E values. What are the E values? Are E values are E equals to generally h nu. E equals to h nu. Here h is the Planck's constant, nu is the frequency. Then E equals to 0, h nu, 2h nu, 3h nu, and so on. Here are E values. Let us consider n number of Planck's oscillators. Develop energy E. N number of oscillators develop the energy E. Then what is the average energy? Average energy is denoted by here epsilon. Then epsilon equals to develop the energy per number of oscillators. So average energy is equals to epsilon equals to total energy upon number of oscillators. So epsilon equals to E upon n. Then energy equals to E equals to epsilon n. So the average energy quantities are 0, epsilon, 2 epsilon, 3 epsilon. So similarly 0, epsilon 1, epsilon 2, epsilon 3. These are energy quantities. Then the total number of oscillations are n, that equals to n0 plus n1 plus n2 plus n3 and so on. So the total number of oscillators, sum of the total number of oscillators is the total number. So here the total energy equals to, first of all, epsilon naught n naught, okay, because epsilon equals to energy equals to, we know that epsilon n, average energy equals to epsilon n. The total energy equals to epsilon naught n naught plus epsilon 1 n1 plus epsilon 2 n2 and so on. Okay, this equation can be written as the total energy equals to 0 into epsilon n naught, 1 into epsilon n1 plus 2 into epsilon n2 and so on. So this equation can be written as epsilon equals, energy equals to E equals to 0 plus epsilon n1 plus 2 epsilon n2 and so on, or epsilon n r and so on. So this is the total energy. According to Maxwell's distribution law, according to Maxwell's distribution law for Planck's oscillations, n r is equals to n naught into e to the power of r epsilon upon kt. This is the Maxwell's distribution law for Planck's oscillations. N suffix r is equals to n naught into e to the power of r epsilon upon kt. From this equation we will write put the 1 instead of r, n1 equals to n naught into e to the power of minus r ante 1 epsilon upon kt. Then n2 is equals to n naught e to the power of minus 2 epsilon upon kt. n3 is equals to n naught e to the power of minus 3 epsilon upon kt and so on. Okay, these total values are substituted in this equation. Already we know that this equation is the equals to 0 epsilon n1 plus 2 epsilon n2 plus 3 epsilon n3 and so on, or epsilon nr and so on. So these values are substituted in this equation. Then this equation can be written as E equals to 0 is the 0, epsilon n1 is the n naught e to the power of epsilon upon kt plus 2 epsilon n2 is the n naught e to the power of minus 2 epsilon upon kt plus and so on, r epsilon nr is the n naught e to the power of minus r epsilon upon kt and so on. So in this equation the total terms have the n naught, the n naught. So here n naught is the common value, so E equals to n naught and also epsilon is also common here. So okay, so this equation, total equation, can be written as e to the power of epsilon upon kt plus 2 e to the power of minus 2 epsilon upon kt and so on, r epsilon e to the power of minus r epsilon upon kt and so on. This equation can be written as this. In above equation, in this equation, this term, instead of this term we put value x, so e to the power of minus epsilon upon kt is equals to x. So in total equation, instead of this term we substitute this value, so this equation can be written as energy equals to n naught epsilon, this is the x, plus this is the 2x square plus 3x cube and so on, r x to the power of r and so on. But already we know that value is x plus 2x square plus 3x cube plus 4x to the power of 4 and so on, r x to the power of r plus and so on. This value is equals to x upon 1 minus x whole square. So instead of this term, in the place of this term we substitute value this. So the energy can be written as n naught epsilon then x upon 1 minus x whole square. Okay, so this value, right, this side, E equals to n naught epsilon upon x upon 1 minus x whole square. From Maxwell's distribution law, what is the value? nr is equals to n naught e to the power of minus r epsilon upon kt. Okay, so now we have to write the n equals to total oscillators equals to n naught plus n1 plus n2 and so on. So some values. So here n is equals to n naught plus n1 is the n naught into e to the power of minus epsilon upon kt plus n2 is the n naught into e to the power of minus 2 epsilon upon kt. Okay, in the total term the common is the n naught, n equals to n naught 1 plus e to the power of minus epsilon kt plus e to the power of minus 2 epsilon upon kt and so on. Already we know that e to the power of minus epsilon upon kt is the x. E to the power of minus epsilon of kt is the x. So this equation can be written as this equation can be written as n equals to n naught 1 plus x plus x square plus and so on. So similarly, this value is equals to, we know that in the intermediate level in the mathematics, 1 plus x square and so on is equals to 1 upon 1 minus x. So in the place of this total term, we substitute this value. Then this value, so here n equals to n naught into 1 of 1 minus 6. No, 1 minus 6. So this value, write this side, n equals to n naught 1 upon 1 minus 6. Now, the average energy, what is the average energy, is equals to epsilon. Epsilon equals to total energy upon total oscillators. So these two values are substituted in this equation. This is the average energy. Average energy is equals to, energy is the n naught epsilon into x upon 1 minus x whole square upon n is the n naught 1 upon 1 minus x. So here n naught are cancelled. So average energy is equals to epsilon x upon 1 minus x whole square into 1 minus x upon 1. So here 1 minus x square is the cancel. Remaining is the average energy is equals to epsilon x upon 1 minus x. Okay, this value can be written as, average energy is equals to epsilon x is the e to the power of minus epsilon upon kt. Here 1 minus x is the e to the power of minus epsilon upon kt. In this term, we take the common e to the power of minus epsilon kt. Average energy is equals to epsilon into e to the power of minus epsilon upon kt. So here e to the power of minus epsilon upon kt is the common. Then 1 is can be written as epsilon upon, not minus, e power epsilon upon kt minus 1. So now epsilon upon e to the power of minus epsilon kt, e to the power of epsilon kt is the 1. E to the power of minus epsilon kt into 1, e to the power of minus epsilon kt. Then this is the cancel. So the average energy is equals to epsilon upon e to the power of epsilon upon kt minus 1. This is the average energy. For first oscillation, so average energy is equals to epsilon upon n. Or first oscillation means n is the 1. For first oscillation, n equals to 1. Then average energy is equals to E upon 1. So then average energy equals to E is the h nu upon 1. So average energy equals to h nu, E equals to h nu, that is the equals to h nu. So then the average energy is equals to, h nu This is the epsilon, average energy. Average energy is the epsilon, h nu upon e to the power of, in the place of epsilon we substitute the h nu upon kt minus 1. Further simplification, this is the total value is average energy is equals to h nu upon e to the power of h nu upon kt minus 1. So this expression represents energy of oscillator. Energy of oscillator according to classical Planck's theory. Classical Planck's theory. This is also Planck's constant. This is also Planck's constant. But we know that the number of oscillations per unit volume between, so the number of oscillations per unit volume between the frequencies nu and nu plus d nu is given by df equals to 8 pi kt into nu square upon c cube d nu. This is the formula. In the previous session, the Rayleigh-Jeans law, the number of oscillations per unit volume between the frequencies nu and nu plus d nu is given by df equals to the difference in frequency, the change in frequency equals to 8 pi kt into nu square upon c cube at d nu. Okay, but the total energy of the radiation associated with Planck's assumptions, Planck's assumptions. So the total energy is equals to frequency modulus of frequency into average energy. Average energy. So the frequency is equals to 8 pi kt, generally minus 8 pi kt, generally minus 8 pi kt in the modulus, the change of positive 8 pi kt into nu square upon c cube d nu. This is the frequency minus the average energy is equals to h nu upon e to the power of h nu upon kt minus 1. So this equation can be written as 8 pi kt nu square into nu square nu cube h d nu upon remaining is the c cube e to the power of h nu upon kt minus 1. So this is the Planck's radiation law. This is the Planck's radiation law. This is the Planck's radiation law. Okay, in the terms of wavelength, so wavelength equals to c upon nu. Generally nu is equals to, c is the velocity, generally velocity equals to nu lambda, v equals to n lambda means v equals to n lambda, v is the the velocity n is the nu lambda. Generally c equals to nu lambda, then nu is equals to c upon lambda. We put this value, put the instead of nu. So this total equation in the terms of wavelength. So in above equation we substitute in the place of this value 8 pi kt. Nu cube is the c upon lambda whole cube, c upon lambda whole cube, h d nu upon c cube e to the power of h in the place of nu, c upon lambda upon kt minus 1. So this equation can be written as 8 pi kt, here c cube upon lambda cube h d nu upon c cube e to the power of hc upon lambda kt minus 1. So here c cube is the cancel. The total energy is equals to 8 pi kt h d nu upon lambda cube. In the numerator it can be changed in the denominator, lambda cube e to the power of hc upon lambda kt, hc upon lambda kt minus 1. This is the total energy at change in frequency. This is the total energy at change in frequency. So this is also Planck's radiation formula. This is also Planck's radiation formula. The total energy can be written as E d nu. Here 8 pi kt h d nu upon lambda cube e to the power of hc upon lambda kt minus 1. So here d nu is the cancel, but it's not impossible. So here nu is the c upon lambda, d nu is the minus c upon lambda square d lambda. So in this place we substitute this equation. So E d nu is equals to 8 pi kth into minus c upon lambda square d lambda upon lambda cube e to the power of hc upon lambda kt minus 1. So modulus, apply the modulus. So E d nu is equals to, total value is in positive, 8 pi kth c d lambda upon lambda square into lambda cube is lambda to the power of 5 e to the power of hc upon lambda kt minus 1. This is the finally Planck's radiation law.